Here's some new technology for you. This is based on some alien technology. It comes up from an idea that NASA's had that they wanted to do but don't know how to do. So we'll see if you know how to do this. Okay, so this is an interesting video. So part 204, line 18.0, Skyhook Space Elevator fuels DS1 Fibre Optics BOTDA, BOTDA, and 5G Wow Seti. There's the alien radio signal there. So I'm going to Google Advanced Fuels New Millennium NASA. The keywords are Skyhook Space Elevator, line 18 OPA3A. The spacecraft eventually ran out of hydrazine fuel for its attitude control thrusters. Many elevator variants have been suggested, all of which involving traveling along a fixed structure instead of using rocket-powered space launch. Most often a cable that reaches from the surface of the Earth on or near the equator to geostationary orbit, GSO, and a counterweight outside of the geostationary orbit. That was the concept for their Skyhook space elevator, but they were never able to figure out how to get it to work. So other things that came up with this, when I Googled this stuff, was Deep Space One. Then the NASA New Millennium program came up. That was my first time actually hearing about it. They tested payload of advanced high-risk technologies. Unfortunately, their spacecraft ran out of hydrazine fuel for its attitude control thrusters. So here's a space elevator. This is the original design they had. Counterweight, center of mass for system above the geostationary level. Then you have the geostationary orbit. Then you have a cable and a climber, an anchor at the equator in the North Pole with Earth. That was their idea of making a space hook. A space elevator for Earth would consist of a cable anchored to the Earth's equator reaching into space. By attaching a counterweight at the end or by further extending the cable upward for the same purpose, the center of mass is kept well above the level of geostationary orbit. Inertia ensures that the cable remains stretched taut, countering the gravitational pull downward. Once above the geostationary level, climbers would have weight in the upward direction as the centrifugal force overpowers gravity. The diagram is to scale. The height of the counterweight varies by design, and a typical workable height is shown. So just so you know, the next 3 videos are going to show you how to build a space elevator based on alien technology. They have an idea for you. It's up to you whether or not it works or not, okay? So you'll be want to look from line O, P, and Q, and R. I guess there's 4 videos, sorry. A space elevator is a proposed non-rocket space launch structure. A structure designed to transport material from a celestial body surface into space. Many elevator variants have been suggested, all of which involve traveling along a fixed structure instead of using rocket-powered space launch. Most often a cable that reaches from the surface of the Earth or on or near the equator or geostationary, and I already read this. I'm repeating myself here. Discussion of a space elevator dates back to 1895 when Konstantin Tsiolkovsky proposed a freestanding Tsiolkovsky tower reaching from the surface of Earth to a geostationary orbit of 22,236 miles up. Like all buildings, Tsiolkovsky's structure would be under compression, supporting its weight from below. Since 1959, most ideas for space elevators have focused on purely tensile structures, with the weight of the system held up from above. In the tensile concept, the space tether reaches from a large mass, the counterweight, beyond geostationary orbit to the ground. This structure is held in tension between Earth and the counterweight like a guitar string held taut. Space elevators have also sometimes been referred to as beanstalks, space bridges, space lifts, space ladders, skyhooks, orbital towers, orbital elevators. While some variants of this space elevator concepts are technologically feasible, current technology is not capable of manufacturing tether materials that are sufficiently strong and light to build an Earth-based space elevator of the geostationary orbital tether type. That's because you guys don't know what I'm going to do. I'm sorry, I'm being smart ass here. Recent concepts for a space elevator are notable for their plans to use carbon nanotube or boron nitride nanotube base materials as the tensile element in the tether design. Since the measured strength of carbon nanotubes appear great enough to make this possible, technology as of 1978 could produce elevators for locations in the solar system with weaker gravitational fields such as the Moon or Mars. For human riders on an Earth-based elevator, adequate protection against radiation would likely need to be provided, depending on the transient time through the Van Allen belts. At the transit times expected for early systems, radiation due to the Van Allen belts would, if unshielded, give a dose well above permitted levels. The orbital space elevator, or geostationary orbital tether, is a subset of the skyhook concept, and is what people normally think of when the phrase space elevator is used, although there are variants. Construction would be a large project. The minimum length of an Earth-based space elevator is well over 36,000 kilometers, or 22,369 miles long. The tether would have to be built of a material that could endure tremendous stress, while also being lightweight, cost-effective, and manufacturable in great quantities. Materials currently available do not meet these requirements, although carbon nanotube technology shows great promise. As with all leading-edge engineering projects, other novel engineering problems would also have to be solved to make a space elevator practical, and there are problems regarding feasibility that have yet to be addressed. So April 19, 2012, 11:38 p.m., these are my thoughts. Again, today is April 27th when I'm actually filming this. So key paragraphs to look at from the Wikipedia quotes. Since the elevator would attain orbital velocity as it rode up the cable, an object released at the tower's top would also have the orbital velocity necessary to remain in geostationary orbit. Unlike more recent concepts for space elevators, Tuscalosi's conceptual tower was a compression structure rather than a tension or tether structure. Building a compression structure from the ground up proved an unrealistic task, as there is no material in existence with enough compressive strength to support its own weight under such conditions. Both the tower and a cable ideas were proposed in the quasi-humorous Adrian column in New Scientist, December 24, 1964. So, the word used, fiber optics, came to mind. So, February 1st, 2012, 11:22 p.m., my thoughts. A cable needed to travel up into space. The thoughts that come to mind is fiber optics is a type of cable wire. So in line 17, T2D, BOTDA fiber optics, Fournier, Sinusoid, molecular vibration, superlumincal energy transport, Wow Seti. In that video, it talks about pulsing the probe wave to reduce non-local effects in Brillouin optical time domain analysis BOTDA sensors. And that was from April 2011. So we propose a simple technique that is able to mitigate non-local effects in Brillouin optical time domain analysis BOTDA sensors. The technique consists in pulsing the probe wave so that the Brillouin interaction only takes place in a portion of the fiber. A shorter interaction length reduces the non-local effects induced by pump depletion. The portion of fiber investigated each time can be easily scanned along the whole fiber length so that the complete Brillouin frequency shift distribution can be retrieved by successive measurements. So that's the end of video O. Again, the next 2 or 3 videos are going to be about the space elevator and the ideas to build it.